Okay, examining Q versus K. The Pac-Man piece will make sense in just a few minutes. If you have a very small value of K, that means that it is making very few products. If you have a large value of K, then at equilibrium, there are very few reactants. So small values of K means that when the reaction reaches equilibrium, there aren't many products. A large value of K means that when the reaction equals equilibrium, there are very few reactants. They're almost all used up. If it's close to a 1, that means it's about equal on both sides. So we're going to use Q, known as the reaction quotient, to determine which way the reaction will shift to reach equilibrium. So most reactions that we look at aren't at equilibrium unless we're told otherwise. So we're going to use the concept of Q versus K. I look at Q as a Pac-Man. I know it's a stretch, but bear with me, and you'll see how this works. So you're going to calculate Q and apply all the rules that you do to K to a Q. Q just means something that's not equilibrium, where K has always meant something at equilibrium. So think of Q and K as the exact same thing, except for Q is when something is not at equilibrium. So up until this set of notes, we have assumed everything was at equilibrium. So what you will do is you will always compare Q versus K. Think of the word OK. So I know Q is not an O, but it kind of think of it as OK. So always do Q versus K. So if Q is less than K, then the reaction is going to proceed from the left to the right. Think of the less than sign as Pac-Man. Which way is Pac-Man heading? To the right. Q greater than K, the reaction is going to proceed from the right to the left. Which direction is Pac-Man facing? Pac-Man is facing to the left, so he's going to go to the left. So less than, facing to the right, goes to the right. Think of Pac-Man eating to the left or to the right. So this shows Pac-Man. If you make this into a Pac-Man, it's going to go to the right. If you make this into a Pac-Man, it's going to chew to the left or eat the dots to the left. When it's equal, it's at equilibrium. How does this apply to a problem? Okay, so a couple things we need to think about is what is the difference between K and Kp in terms of how you set up the expression? Nothing, other than when we set up K and Kp, remember that K, so the difference between K and Kp really is nothing. So the difference between K and Kp and the expression is just how you set it up. Remember that K would have square brackets over square brackets. These would be the products, and these would be the reactants. Kp, instead of square brackets, remember square brackets were moles per liter, so concentration, and Kp is going to be the pressure of the products over the pressure of the reactants. Pressure of the reactants. So pressures in Kp and square brackets are with K. We still put the products, the product of the products, so we multiply the products over the product of the reactants, so we multiply the reactants on the bottom. Same thing with Kp. Instead of having moles over liters, we might have atmospheres or millimeters of mercury or torr, kilopascals. Well, we would take the pressure of the products, so we multiply the pressure of the products over and then divide by the multiplication of the pressure of the reactants. This should not feel new to you. We've been doing this for quite a while now. So this asks about the numbers. For K, we're plugging in moles over liters. For Kp, we might plug in ATMs, millimeters of mercury, torr, too many A's there, kPa. Okay. This next thing asks, the next question says, what is the difference between Q and K in terms of how you set up? Nothing. Nothing. Same set of rules. I can do a Q or a K. I would follow this. Or I can do a QP or a KP. Follows this idea. So Q and K are the exact same thing. Q just means not equilibrium. K means at equilibrium. So going forward, if we're not told it's equilibrium, we have to assume it is not. When do we need to use Kp equals KRT delta N? When we're given one and asked to solve the other. Same thing for Q. If we were given Q and asked for QP, we'd have to use this relationship, just like we did with K and Kp, or vice versa. If we're given Kp and asked to solve for K, then we have to use this relationship. Okay, we will look at this a little bit more in detail later. We're not going to deal with this yet. That's coming. We're going to look at this example first. Let me clean that up. Okay, so it says predict the direction. So anytime it asks you to predict a direction, you're going to use that whole idea of Pac-Man. So here's my Q versus my K. Remember, whichever direction my greater than or less than sign is, which direction it's going to shift, or the direction we're going to predict. Okay, so here it says predict the direction in which reactions will occur to reach equilibrium, starting at 0.1 moles of N2O4 and 0.2 moles of N. Okay, so we are going to first have to figure out K. Why? Because we are given concentration and we're given Kp. So first we're going to have to figure out K. So we know Kp equals K RT delta N. So we're going to say 11 equals K, which we don't know, 0.08206 times 373. Remember, that comes from the fact that this is 100 plus 273.16. That's how I get the 373. My delta N, if you think about it, remember delta N, we'd split the reaction and we say 2 on this side total moles and 1 total mole here. We take products. 2 minus 1 gets me a 1. So then we're going to calculate this. Okay, so when I did that on the calculator, I got K equals 30.6. 11 is still here, so now we're going to take 11 divided by 30.6, and I get K to be 0.359. Okay, so that's just reviewing how K and Kp are related. So now we can come up here and we can say our K is 0.359. I'm going to go ahead and get rid of that because that's technically K. Okay, so that's how we go from Kp to K. Now, why was I worried about Kp versus K? Well, I know that if I'm going to use Kp, then these all have to be units of pressure, and these aren't. These are going to get me units of concentration. So I had to get my K so that I have K later for this. Okay, so that's how you would figure out whether you need K or Kp. Look at the units that are in your problem. Are they pressure units? Then yeah, you can just stick with this Kp. But if they're not pressure units, then you're going to have to get them converted, Kp converted to K, because you have units that'll get you to concentration. Okay, so that's just the first piece. We have not even thought about Q, because Q, remember, get rid of this here. Q is the same thing as K, except for it's before equilibrium. So we're going to treat Q just like K. But remember that in order to have a Q or a K, we have to have concentration. So we're going to figure out what is the concentration of NO2. And we're going to do that first. So let's think about that. That's moles over liters, if you remember from the first part of our unit. So we're going to take moles of NO2 was 0.20. So I'm looking right here. And it's going to be divided by 2.0 liters. Okay, I'll get that calculated here. Let's try that on our calculator. So 0.2 divided by 2 is 0.10 molar. We're also going to calculate the concentration of N2O4. Why are we worried about concentration? Remember, we're doing K or Q. A K or Q must have moles over liter. So we're going to take 0.10 moles. I should have put moles up here, my mistake, over 2.0 liters. So 0.1 divided by 2 is 0.05 big M. Okay, so now we can set up our Q. Our Q is the same as before. We're going to take NO2 squared, my products, over my reactants. There's a 1 here, so there's no power. So I can calculate Q. I got to grab the correct number, 0.10 squared over 0.05. So 0.1 squared divided by 0.05, and I get this to be 0.20. So then we're going to be able to look at now Q versus K. So Q was 0.20 We know K was 0.359. So then we know this sign would go here. Think of this as Pac-Man. I know, aren't I artistic? So we know it's going to shift right because Pac-Man is heading to the right. Okay, let me go through quickly what we did again. First thing I observed is that I have a KP. I have to have K. Perhaps in your homework examples in your notes, maybe you already had this, I'm not sure. Remember, there is a copy of these notes in the beginning of this unit on Schoology. So if you have units of pressure and you have KP, you're good to go. But if you do not have units of pressure and you have a KP, then you're going to have to convert to K as I described in the beginning of this problem. So we did that. That's how we get the 0.359 here. To get Q, we do just like what we would do with K. We set up products over reactants. Remember, we leave out solids and liquids. We can only include gases and aqueous. These were both gases, so they were able to be included. I had to first calculate their concentrations because remember that Q and K mean square brackets, which means moles over liter. So I calculated 0.1 and I calculated 0.05 and I plugged them in, and I had to raise NO2 to the second power because there's 2, and N2O4 was to the first power because there's only 1. I plugged it in, got that, and then I looked at Q versus K, and I saw that I had a greater than sign because 0.2 is less than 0.3. I'm sorry, I had a less than sign. 0.2 is less than 0.3, so Pac-Man is heading to the right, so it shifts to the right. Okay, so here we have another problem. In this case, we have a KP given, but we have pressure units. ATM is a pressure unit, so we don't have to worry about converting between K and KP. We do know, however, that we want to eventually at some point here compare QP versus KP. Remember, the P just means pressure. Q and K are the same thing. One means not at equilibrium, K means at equilibrium. So then we're going to think about what our QP would be. It's going to be the pressure of CO squared. Here's my product. There's 2 of them. It's a gas, so it's okay to include. And then the pressure of CO2 to the first power, I would not put in this because it's a solid. So then I look for the pressure of carbon monoxide, so 0.00015. I'm going to have to square that over the pressure of carbon dioxide, 0.010. I'm going to go through that math. Let's do that. 0.123, 3 zeros there. 15 squared, divide by 0.01, and I get, I'm going to put this in scientific just for purposes of writing it, 2.25 times 10 to the negative 6 for my Q. So I'm going to put that in here, 2.25 times 10 to the negative 6. And we're going to look at our KP, 1.17. So this is definitely way bigger. So then it's going to shift to the right, because that's the way my Pac-Man is heading. Okay, on this example here, notice I see the word equilibrium everywhere, so be very careful. I wasn't pointing that out as best as I could because it asks us for shift. So if it asks us for shift, we know it's not at equilibrium, or it wouldn't ask us for shift because it'd already be there. In this problem, it doesn't say anything about shift. It talks about the word equilibrium everywhere. So therefore, we do not need to worry about Q. In this problem, it's asking us to figure out the equilibrium pressure of NO2. So let's look at what our expression would look like. Our expression would be Kp equals NO2 squared over N2O4. Now remember, both of these can be included because they're in the gaseous phase. So what do we know? Well, we know Kp is 0.133, and we know the value of N2O4. So we don't know this value. But from the word problem, I can see the pressure of N2O4, so this is 2.71. So now I'm going to solve this by multiplying these two numbers. So 0.133 times 2.71, and I get on my calculator 0.360 equals NO2 squared. So I'm going to take the square root of both sides. So I'm going to square root that, and I get 0.60 is equal to the concentration of NO2. Now, why did I ignore Q? Because everywhere in this problem I see the word equilibrium. So it's very important that we read our problems and decide, is it talking about shift then I have to do Q versus K. If it has the word equilibrium, then I'm not looking at Q versus K. I'm probably just solving for a piece of my expression like I did here. So this is the first part of part 2 of equilibrium. I want to just remind you that when do I use Q versus K? I use Q versus K when I'm asked about shift. So if it asked about the shift or which direction the reaction would proceed to equilibrium, then you would use Q versus K. If you see the word equilibrium pretty much throughout the problem, you're probably doing a problem similar to this, where you're solving for one of the pieces of the expression. In this case, we solve for NO2. More to come.